A jet engine doesn't move an airplane by grabbing the air in front of it. It moves the airplane by taking air in, accelerating it backward, and turning that invisible flow into thrust. Stand beside a runway during takeoff, and you don't just hear the engine, you feel it. The low roar shakes the ground. The fan blades at the front blur into a dark, spinning disc, pulling calm air into the mouth of the engine and turning it into a controlled stream of power. Inside that metal cylinder, air is squeezed, heated, and fired backward with enough force to push hundreds of tons of aircraft down the runway. The airplane begins to roll, then surge, then lift. Not because the engine is throwing flames like a rocket, but because it is moving an enormous mass of air. So before we look at the fire, we have to follow the air. Because a jet engine is not really a fire machine first. It is an air machine. In this video, we're focusing on the kind of jet engine most passengers actually see under the wing, the modern turbofan. Not every jet engine is built the same way. Some are built for extreme speed. Some turbine engines drive helicopter rotors, and some are designed for military aircraft. But the turbofan is the engine that carries millions of people across the world every day. To understand how it works, we'll open the engine from front to back. First, the intake captures the air. Then, the fan splits that air into two paths. The compressor squeezes part of it. The combustor adds fuel and heat. The turbine steals energy from that hot gas. And finally, the exhaust and bypass air create the thrust that pushes the aircraft forward. At the heart of every jet engine is a simple rule. If you push something one way, you get pushed the other way. You can see the same idea in a balloon. Let it go, and air rushes out the back while the balloon shoots forward. A jet engine is not that random, but the physics is the same. Thrust is not magic. It is momentum. Push air one way, and the airplane is pushed the other way. Fuel matters because it adds energy. But the engine's real job is not just to burn fuel. Its real job is to take air that is sitting almost still in front of the aircraft, speed it up, and throw it backward in a controlled stream. That backward moving air becomes forward force on the aircraft. That force is thrust. But here is the real question. How does a metal machine take ordinary air from the sky and turn it into a powerful stream strong enough to move an airplane? The first thing the air meets is the intake, the wide, rounded mouth at the front of the engine. From the outside, the air looks calm. But at the mouth of the engine, it is being pulled into a spinning wall of blades. The fan is not there for decoration. It is the first major controller of the airflow. As those huge blades rotate, they grab an enormous amount of air and pull it inward. Standing too close to a running engine is dangerous for the same reason. The intake does not gently breathe air in. It can drag air, dust, tools, and anything too close toward the spinning fan. But the fan does more than swallow air. It organizes it. Some of the air is guided toward the engine core, where it will be compressed, mixed with fuel, and burned. The rest will flow around the core through the bypass path. At this point, the air has only begun its journey. It has entered the machine, but it has not yet become powerful. For that, it must be squeezed. After the fan, the air that enters the core reaches the compressor. A long tunnel of blades arranged in stages. Each stage has two jobs. First, rotating blades spin at high speed and push the air deeper into the engine. Then, stationary blades, fixed in place, straighten and slow that flow just enough to raise its pressure before it reaches the next spinning row. The compressor does not simply blow air forward. It squeezes it, stage after stage, until invisible air becomes a dense, pressurized charge ready for combustion. As the air moves through this narrowing path, it changes. Its pressure climbs, its temperature rises. What entered as ordinary atmosphere is now packed tighter and tighter, like a spring being compressed inside a metal tube. But this airflow has to stay disciplined. Inside a jet engine, air cannot tumble randomly or break away from the blades. If the flow becomes unstable, the compressor can stall or surge. In extreme cases, the flame in the engine can even go out. So, the compressor is not just a set of spinning fans. It is a carefully shaped pressure machine, preparing the air for the next stage, controlled fire. The compressed air now enters the combustor, one of the most violent places inside the engine, but also one of the most controlled. Fuel is sprayed into the fast-moving, high-pressure air as a fine mist. Then it ignites. But inside the combustor, the engine is not exploding. It is holding a controlled fire in place while air races through it. That difference matters. An explosion would be sudden and destructive. A jet engine needs something steadier, a continuous flame that keeps adding heat to the airflow without stopping it. As the air passes through this fire, heat is added rapidly. The air expands, speeds up, and turns into a high-energy river of hot gas rushing toward the back of the engine. When the pilots ask for more power, the engine does not simply spin faster by magic. More fuel is added, more hot gas is produced, and the turbine has more energy to extract. That lets the fan and compressor move more air, and that larger, faster-moving airflow gives the aircraft more thrust. But if all of that hot gas simply left the engine without giving some energy back, then nothing would keep the fan and compressor spinning at the front. So, before the gas can leave the engine, it has to pass through one more critical part: the turbine. The turbine sits in the path of the hot gas like a set of metal windmills built for extreme heat. As the gas rushes out of the combustor, it slams into rows of turbine blades and forces them to spin. But the turbine is not just sitting there to slow the gas down. It is taking energy from that gas and sending it back to the front of the engine. The turbine steals just enough energy from the hot gas to keep the compressor spinning, and the compressor feeds the fire that keeps the turbine alive. This is the loop that makes a jet engine feel almost self-sustaining. The compressor pushes air into the combustor. The combustor adds fuel and heat. The hot gas spins the turbine, and the turbine, through a shaft running down the center of the engine, drives the compressor again. In many modern turbofans, not every blade row spins at the same speed. Different sections can rotate on different shafts or spools, so the fan, compressor, and turbine can each work closer to their ideal speed. Once the engine is started, this cycle repeats continuously. Air feeds fire. Fire drives turbine. Turbine drives compressor. Compressor feeds more air. But even after the turbine takes its share of energy, the engine still has one job left: turning that moving air into useful thrust. At this point, the engine has compressed air, burned fuel, and used the turbine to keep itself alive. But thrust comes down to one simple rule. In simple terms, thrust depends on two things: how much air the engine moves and how much it accelerates that air backward. You can make thrust by taking a small amount of air and throwing it backward very fast. That is closer to the idea behind older, pure jet engines. But you can also make thrust by moving a much larger amount of air and changing its speed more gently. For passenger aircraft, that second method is extremely important. More thrust does not always mean more fire, more heat, or a louder blast from the core. Sometimes it means moving more air around the core. And that is where the modern turbofan becomes surprising. The biggest twist is this: In a modern turbofan, much of the air that helps push the airplane forward never touches the fire at all. When the front fan pulls air into the engine, the flow splits into two paths. One path goes into the core. This is the smaller inner stream. It moves through the compressor, enters the combustor, mixes with fuel, burns, spins the turbine, and leaves as hot exhaust. But the other path is the bypass stream. This air is pulled in by the same huge fan, but instead of entering the hot core, it flows around it through the outer duct. It is still accelerated backward. It still creates thrust, but it does it without being burned. That is what bypass ratio means. It compares how much air goes around the core to how much air goes through the core. So, when you look at a modern airliner engine, you are not just looking at a tube full of fire. You are looking at a giant fan wrapped around a smaller gas turbine. The hot core is the power generator. It keeps the fan spinning. But the fan moves a massive amount of bypass air, and that air provides much of the push. This is why modern passenger engines look so wide. They move more air efficiently, instead of simply blasting a smaller stream of hot gas at extreme speed. And that changes how we think about jet engines. The fire matters. But the real secret is the air. Where it goes, how much of it moves, and how precisely the engine controls it. Once you understand bypass air, the size of modern engines starts to make sense. A bigger fan can move more air without throwing it backward at insane speed. And that is one reason modern engines have grown so enormous. For a passenger aircraft, this matters because efficient thrust is not just about brute force. If the engine can move a larger mass of air more smoothly, it can create the push the airplane needs while using fuel more efficiently, and often making less noise than a smaller, faster exhaust stream. That is the logic behind high-bypass turbofans. The hot core still matters because it powers the system. But the large front fan does much of the visible work, pulling in a huge volume of air and sending much of it around the core. Some engines have become almost hard to believe in scale. The GE9X, built for the Boeing 777X, has a front fan more than 11 feet across. Standing in front of an engine like that, you are not looking at a small machine with flames inside. You are looking at a giant air pump attached to a precision turbine. But if a bigger fan is so useful, why not keep making it larger forever? Because at that size, air is not the only problem anymore. The fan itself becomes the challenge. A fan can only grow so far before the engineering starts fighting back. The first limit is simple: ground clearance. An engine under the wing still has to fit above the runway. If the fan gets too wide, the aircraft may need longer landing gear, a different wing design, or an entirely new shape. But the bigger problem is speed. The larger the fan becomes, the more violent the outer edge becomes, because the blade tip has to travel a much longer circle every rotation. Near the center, the blade is moving through a smaller path. At the tip, it is racing around a much larger one. That creates enormous stress, pulling the blade outward with every revolution. The fan has to be light enough to spin efficiently, but strong enough to survive that force. This is why modern fan blades use advanced lightweight materials and careful shapes. They also have to survive real-world threats, including bird strikes. Engineers test engines for that, because a bird entering the fan at high speed cannot be treated like a small problem. Some modern designs even use a gearbox, allowing the big fan to spin slower while other parts of the engine spin faster. But every solution adds complexity. And after the fan, the engine faces an even harsher challenge: surviving the heat inside the core. Inside the engine core, the air is no longer just moving fast, it is carrying intense heat. The hot gas leaving the combustor rushes straight into the turbine, and those turbine blades have to stand inside a controlled storm of heat, pressure, and speed. This is one of the hardest problems in the entire engine, because metal alone is not enough. If ordinary metal sat in that flow, it would weaken, deform, or fail. But turbine blades are not ordinary pieces of metal. They are made from advanced heat-resistant materials, shaped with extreme precision, and protected by special coatings that help shield them from the hottest gas. The hottest part of the engine survives because it is not just strong. It is cooled from the inside. Some of the compressed air from earlier in the engine is not sent directly into the fire. Instead, it is carefully routed through tiny passages inside and around the turbine blades. That cooler air forms a protective layer, helping the blade survive while hot gas screams past it. So, the turbine is doing two impossible-looking jobs at once. It is extracting energy from the gas to keep the engine alive, while also surviving conditions that would destroy simpler materials. This is why modern jet engines are so difficult to build. The power is not just in the fire, it is in controlling the heat without letting the machine tear itself apart. But even with all of this engineering, the engine cannot begin the cycle by itself. Before air feeds fire, and fire drives turbine, something has to give the machine its first spin. Before a jet engine can power itself, something else has to give it the first breath. At rest, the fan is still. The compressor is not pushing air, the combustor has no steady flow to burn in, and the turbine cannot spin until hot gas reaches it. So the engine needs help. On many aircraft, that help comes from the APU, the auxiliary power unit, or from external equipment on the ground. The starter begins turning the engine, slowly at first, then faster. The compressor starts pulling air into the core and building pressure. Only then is fuel added and ignited. A small fire becomes a steady flame. Hot gas begins to flow through the turbine. The turbine spins harder. The shaft turns the compressor, and the engine starts feeding itself. At that moment, the starter can let go. The engine has become self-sustaining, breathing air, burning fuel, and keeping its own cycle alive. There is one small detail on many jet engines that most passengers barely notice: the spiral painted on the center of the fan. That small spiral on the nose of the engine is not decoration. On the ground, it is a warning that the machine is alive. When the fan is spinning fast, the blades can blur into a nearly invisible disc. For ground crews working near the aircraft, that can be dangerous. The spiral makes rotation easier to see even from a distance. It is a simple visual signal. Stay clear. The engine may look still from the side, but if that spiral is moving, the intake is active, the fan is turning, and the air machine under the wing is awake. So when you look at a jet engine from the outside, it may seem like a simple metal tube hanging under the wing. But inside, the journey is incredibly precise. Air enters through the intake. The fan divides it into two paths. Part of it goes into the core, where the compressor squeezes it, fuel is added, and controlled fire adds heat to the airflow. That hot gas spins the turbine keeps the compressor and fan spinning, and the fan moves a massive stream of bypass air around the core. Together, the hot exhaust and the bypass air accelerate backward, and the aircraft is pushed forward. A jet engine works because it turns invisible air into controlled force. Again and again, without tearing itself apart. What looks like a fire-breathing tube under the wing is actually one of the most precise air machines humans have ever built. That same airflow can even be redirected during landing to help slow the aircraft down. But that is another story. So the next time you see that engine spinning outside your window, remember, it is not just burning fuel, it is shaping the air. For more breakdowns like this, subscribe, and tell me what machine we should open up next.